Kia ora koutou. In this video, I'm going to go really slowly through this old exam question from 3 years ago. It's an excellence question about two parabolas. And if you start off by just looking carefully at the structure of the two parabolas and then thinking about what the graphs of those two parabolas would look like, I think this question becomes much, much more doable. Okay, so let's just firstly read it through really slowly and see what's going on. Right, consider two parabolas. Well, parabola 1 has this equation, y is equal to ax squared plus bx plus c, and parabola 2 is given by this equation, y is equal to dx squared plus ex plus c. So we're given those two parabolas in expanded form, and we know from level 1 tables, equations and graphs that the most useful piece of information that we get out of expanded form is the y-intercept, right? So we don't know very much yet about these parabolas, but it's our job to find some stuff out. So let's just quickly just sketch what a parabola looks like in expanded form. So suppose I've got ax squared plus bx plus c, and then the second one is dx squared plus ex plus c. Now you didn't have to notice this to get into this question, but when I look at that, as soon as I look at the plus c's, that tells me that what I'm trying to do here is work with two parabolas that have got the same y-intercept. For example, we might have a parabola that looks like that and a parabola that looks like this. Both of them go through that same point on the y-axis. So when x equals 0, y is equal to c. So let's go back and read the question and see what it's asking us to do. The algebra in the question is actually not that hard, but if you don't have that graphical understanding, it's hard to get the whole way through to the end. Right, use algebra to determine the restrictions on the values of a, b, c, d, and e that would ensure that the parabolas meet at two distinct points. So I've drawn a few different situations in GeoGebra with this, but you can play around with this just with pen and paper. And actually, I'm going to do that now so that you see that even a really bad sketch can help you get into a problem like this. So let's just whack in some axes before we start to play with the question. If you don't want to watch this bit, that's fine. But I think for most people, the hardest thing with excellence problems in maths is knowing where to start. And drawing a graph is always a good idea. So here's one parabola here that's going through point C. Now let's draw this so that we get two points of intersection. So let's draw an upside down parabola. Well, you can see, I'm going to change pen, that I've got a point of intersection here and I've got another one here. So there we've got two situations where, let's see the wording. So the parabolas meet at two distinct points. Well, yes, they do in that case. Well, let's get rid of this one. Let's draw another one. So the first one is here, so it's going through here. What if I draw a parabola that looks like this? Right, does that go through twice? Yep, that one goes through twice. So let's start now to think about where we might not have it go through twice. So we'll draw another parabola. This is the y-intercept here. If we had one where we had it like that, that would only touch and that would be once, right? And the other thing that we might have happen is that we could have one that looks like this. So I'm actually going to jump now to the GeoGebra ones. So this graph is showing us one where it touches twice, right? Two meeting points. This is one where it goes through twice. This is one where we just have one intersection, right, where one of those graphs is tangent to the other. And then here's one where it cuts through once, but once only. So what we're going to do now is we're going to do a little bit of algebra to figure out what describes these different situations. And this part is really not that hard. Okay, so to find where the parabolas meet, we know that the y values will be the same. So we just set up this. We've got ax squared plus bx plus c is equal to dx squared plus ex plus c. Now a, b, c, d, and e are all just constants, they're numbers. So we're going to do our usual kind of year 9 stuff to both sides of the equation. I'll start by subtracting c from both sides. that leaves me with, on this side, ax squared plus bx is equal to dx squared plus ex. What I did next is I collected up all my like terms. So I had ax squared plus bx, take away dx squared, take away ex equals 0. Now I'm going to solve this quadratic. I get a minus d x squared plus b minus e x. So all I'm doing in this step is collecting up my like terms, right? Because I've got ax squared here, take away dx squared here. Now I'm down to a quadratic, and it's a quadratic where the constant is 0. So I've got x squared here and x here. So to solve this, my common factor is x, and then it's going to be x into a minus dx plus b minus e. Right, so let's look at what that's telling me about solutions. We know that when we have a quadratic in this form, suppose we have a really easy one like this, this means that either x is equal to 3 or x is equal to negative 5. Well, this one we've got here works in the same way. It's just that we have a, b, d, and e instead of constants. Either x is equal to 0 or a minus dx plus b minus e is equal to 0. This one we'll just leave like that. Rearranging this, we get a minus d x is equal to e minus b, right? Subtracting that from both sides. And now we get x is equal to e minus b over a minus d. So what we're asked is, when will we get two solutions? So we'll get two solutions when x is equal to 0 and x is equal to e minus b over a minus d produce two numbers. And that's going to be most of the time, right? What we can see in all of these graphs is that there is going to be a point where the curves are equal at x equals 0 every time. But in this graph, that's going to be the only time that happens. And in this graph, it's going to be the only time it happens as well. In this graph, we've got one solution where x equals 0, and we've got this other solution here, right? And so this is happening when x is equal to e minus b over a minus d. And in this one here, we've got this one when x is 0, and this one when x is equal to e minus b over a minus d. So what we want to do now with the algebra is go back and say, well, when are we going to get two different numbers here? Well, the first thing to notice is that we're not going to have a second solution if a is equal to d. So if a is equal to d, then x equals 0 is going to be the only solution, because this is going to be undefined. And then there's one more thing that can make us not get two numbers, and that's if this one is also equal to 0. So if a is not equal to d, but e equals b, then we have x is equal to e minus b over a minus d is equal to 0 as well. Okay, for example, if we had 2x squared plus 4x plus 3 and 2x squared plus 6x plus 3, then we've got a is equal to 2, b is equal to 4, d is also equal to 2, and e is equal to 6. So this is the first case here, right? We get x is equal to 6 take away 4 over 2 minus 2, which is undefined. We can't divide by 0. And that's this graph here. I just need to find the right one. 2x squared plus 4x plus 3. Hang on, where is it? It's this one here. Okay. And then the second situation is one where we've got A and D are not equal. So these two numbers are different, but E and B are equal. For example, if we had 3x squared plus, I'm just going really slowly here, plus 4x plus 3, and we had 2x squared plus 4x plus 3, then we're going to get just one solution there, right? Because we've got this matching up here, but we've got different slopes here. So you can play around with that in your graphics calculator and see what's going on. But what you had to do for a full excellence answer here is to explain that you'll get two solutions in all other cases. So let's just sum up where we've got to. I'll get rid of this mess. So if these two things aren't true, we get two solutions. And we'll have x equals 0 and x is equal to e minus b over a minus d, and that will be not the same as 0. Okay, I'm just going to delete a big bit of mess I've put in here. I was trying to do this a different way, but I think that I'm just going to stick with the one way. So really nice question. Lots of these excellence algebra questions are very abstract, and the key to them is often to do what we did here and link up what you know about graphing with what you can do with algebra. They will also almost always come down to difficult quadratic situations. This one actually wasn't a very difficult quadratic, but to understand what was being asked, you had to have a really good understanding of parabola graphs and how that links back to the algebra. Thanks for watching. Sorry that this was really long, but I wanted to give you a long explanation of how to think about what the problem was asking for.